Okay, 4.3, monotonic functions in the first derivative test. Monotonic is just a fancy word saying things go one way. This is going up, and this is going down, this is going sideways. And so when they talk about monotonic, they don't necessarily mean on the full function, they mean on intervals. This is going up on this interval, this is going down on this interval, this is going sideways. Now we want better words besides up, down, and sideways. So we got some definitions. Again, what I like to refer to as graphical definitions, visual definitions. These certainly aren't the official mathematical definitions. There are official mathematical definitions of increasing, decreasing, and constant. If you're interested in them, they are in your textbook. If you're interested in them, you can discuss them with me. But for most of our work, it's beyond what we really need to know. So, definitions. Graphically, a function is said to be increasing on the interval if the graph rises on that interval from left to right. A function is increasing if its graph, as we travel it from left to right, is rising. Graphically, a function is said to be decreasing on an interval if the graph falls that interval, left to right. So if the graph is falling on the interval from left to right, it's decreasing. And then lastly, graphically, a function is said to be constant on an interval if the graph is horizontal on the interval. So shown below is the graph of a function y equals f of x. Find the intervals on which f of x is increasing, decreasing, and constant. Now, I said this once before when I gave you a horrible, horrible graph like this, and I'm going to say it again. Horrible graph because I have no tick marks on the y-axis and I have very few tick marks on the x-axis. You cannot give me graphs without tick marks. They are meaningless without tick marks. I wish I could say I would stop giving things like this, but this was easy to draw. So that's what we did. Easy to draw. Okay, so increasing. Here's where this guy is increasing. INCR stands for increasing. And so it's increasing right to that number 3. So we say that this is increasing, and we'll write it out in words first, on the left forever to x equal 3. So as an interval, negative infinity to 3, with a open parenthesis. We don't include 3 because that's where it's changing. Then on here in yellow, that's where it's decreasing. DECR will always stand for decreasing. And so this is decreasing from x equal 3 to x equal 9, or the interval 3 to 9. Again, parentheses. And then lastly, we're constant. And we are constant. Should spell that right. That's still not how you spell constant. Let's try again. From x equal 9 to the right forever. And so that would be the interval 9 to infinity. So there's what we have: increasing, decreasing, constant. Notice it has nothing to do about the y-coordinates. When we talk about functions being increasing, decreasing, constant over some sort of interval, that's always over over or under the portion of the x-axis in which it's increasing, decreasing, constant. It's always, these are the portions of the x-axis that the function is increasing, decreasing, or constant. Okay, we're going to have the same picture, a slightly different question. Shown below is the graph of a function y equal f of x. Find the intervals on which f prime of x is positive, negative, and 0. So again, let's remember what the derivative means. F prime of x positive would mean the slopes of the tangent lines are positive. So something that looks like that or that, those have positive slopes. So when I look at my graph here and I find where I have positive slopes, well, there'd be a positive slope. There'd be a positive slope. There'd be a positive slope. And so it looks like there are all my positive slopes up there. Going on the next one, f prime of x negative would mean the slopes of the tangent lines are negative. So something that looks like that or that, those have negative slopes. So if I go back over here, there would be a negative slope. There, pretend it touched it, but there would be a negative slope. I could probably do that a little bit better. There would be a negative slope. There would be a negative slope. There would be all my negative slopes. And lastly, f prime of x 0, well, that'd mean horizontal. Slope 0, let's put it this way, slope 0 so horizontal. So here. So I marked it up. Positive slopes in red. Positive f prime of x. Negative slopes in yellow, negative f prime of x. And in green, f prime of x equals 0. So I marked that graph all up. And let's compare that to the previous page where I marked it up increasing, decreasing. Gee whiz, Ms. Browson actually used the same color. There is a complete correlation here. Positive slopes went with where my function was increasing. Negative slopes went where my function was decreasing. Zero slope went for it to be constant. And that is an absolute, honest to goodness, true fact. If a function has a positive slope on an interval, the function is increasing. I said positive slope, meant positive derivative, same thing, positive slope, but positive derivative, increasing, negative derivative, decreasing, zero derivative, constant. And that gives us our first theorem down here. If f prime of x is greater than 0 on an interval, then f of x is increasing on the interval. That is, if f prime of x is positive on an interval, the function is increasing. F prime positive, f of x increasing. If f prime of x is less than 0 on an interval, then f of x is decreasing on the interval. That is, if f prime of x is negative on an interval, f of x is decreasing. Derivative negative, f of x decreasing. And then finally, if f of x equals 0 on an interval, the function is constant on the interval. F of x 0, f of x constant. So what we're doing here, or what we will be doing, is using the derivative to find out about the original function. If the derivative is positive, the function is increasing. If the derivative is negative, the function is decreasing. And if the derivative is 0, the function is constant. You need to know these facts. These are important. Memorize. Okay, so we got that new little piece of information. Then recapping something we already know, but it's very important, so we'll recap it. Locate each local extreme, locate each critical number. So we will do local extremes in blue. So there's a local max. There's a local min. A max, I'm going to stop writing the word local. Min. Now here, some people want to say that there's a local min here maybe, and it somewhat depends on who you're talking to, but in my opinion there's not, because it's coming down and then going sideways. That a minimum should be the bottom of a valley, the maximum should be the top of a mountain. Now, some people like to make different statements about the endpoints, which is why I didn't put endpoints on here. But nothing in there is going to be a local max or min. Okay, so there are those guys. Critical numbers, critical points. In red. And let's recall, that's where f prime of x equals 0. In red. F prime of x equals 0, or f prime of x does not exist. Okay, equal to 0. Those are going to correspond to all your horizontal tangents. There's what I wanted. Horizontal tangents are things that are just horizontal. So right here, that'd be a critical point. CP for critical point, because I could have a horizontal tangent here. Also right here, CP, because that's just coming down and going up. It's not a sharp point. CP there, that'd be a horizontal tangent. And then all the way in there, all of those would be critical points. Every single guy in there would be a critical point, because the slope would be 0. And then here, this is going to be a critical point. Specifically, the derivative does not exist, because I have a corner point. And so we saw something like this before, where we note that everything in blue is also marked in red, but not all the red is blue. And so a little recall here. All local extremes occur at critical numbers or critical points, but not all critical numbers yield local extremes. And that's just what I'm trying to remind you of there, of the relationship between critical points or critical numbers and local extremes. All local extremes come from critical numbers, but not all critical numbers are local extremes. We've already practiced finding critical numbers. We've done that. And so when you find a critical number, what you're finding are the possible locations of local extremes. Possible locations. We don't know for sure that they are locations. And so we need a way to take those possible locations of local maxes and mins and verify whether indeed it's a local max, a local min, or nothing at all. And that way to classify our critical numbers as local maxes or min will be the first derivative test. First derivative test says this. Let C be a critical number of a function f of x. So you already have all your critical numbers. Now it's time to classify them. If f prime changes from positive to negative at x equals c, then there's a local maximum at x equals c. If f prime of x changes from negative to positive at x equals c, then there's a local minimum at x equals c. If f of x does not change signs at x equals c, then there is no local extreme at x equals c. There's the official statement of the first derivative test, and it's talking about changes in your derivative. So if you start with your critical numbers, then if you find that your derivative changes from positive to negative at that critical number, you have a local max. If your derivative changes from negative to positive at that critical number, you have a local min. And if you don't see a change, you have no local extreme. First derivative test. Now that is the official statement of the first derivative test. That's what you'll see in virtually every calculus book. It is true, but it's not very visual. So I like to do a more visual form of it, which we will do on the next video.